One of my colleagues, to motivate me to not talk too long, said he was going to be sitting back there with a cold German beer that I could have as soon as I finished my presentation. So I'm motivated. Also, I think I'm going to hold the screen just to... Yeah. So I'm going to use this figure throughout my talk to try to motivate how we can relate quality control, planning, and design to the ultimate safety or risk of harm to a patient. This is kind of a redo of a figure that's appeared in the new CLSI EP23 document. So the idea here is the sequence of events that can lead to harming a patient or causing an unintended consequence in a patient. Some failure mode occurs somewhere in the testing process that leads to an out-of-control condition. Depending on that size and the type of out-of-control condition, that can lead to an unreliable, one or more unreliable patient results being produced, which may or may not lead to unreliable patient results being reported. At that point, the risk of reporting an unreliable patient result is kind of where our control of the process ends. That's what we can try to manage. And then there's some chance that an unreliable result that we report will lead to an incorrect action by a caregiver. And then there's some chance that that incorrect action might lead to an unintended consequence for a patient. I would argue that what we do traditionally in designing and implementing statistical quality control is what's contained in that green shaded area. We start with the occurrence of an out-of-control condition, and depending on the size and the type, there are a few types. We can think of an out-of-control condition that only affects a single patient sample, an out-of-control condition that affects a batch of patient results, an out-of-control condition that, when it occurs, will persist and continue to affect all patient results produced until we detect that there's a problem and do something about it. And an out-of-control condition could be of small magnitude or it could be of large magnitude. Depending upon the type and the size of the out-of-control condition, and depending upon what kind of quality control processes we have in place, some number of unreliable results will be produced. And depending upon how and when we report results, some number of unreliable results will be reported. The decisions we make about how we do quality control is all about managing that part of the process and trying to manage the risk of producing and reporting unreliable patient results, right? So if we're going to talk about the risk of reporting an unreliable patient result, we have to define what we mean by an unreliable patient result. ISO 15189 tells us that we need to assure that patient results meet the quality required for their intended use. So we have to define what that means to us. And a classic way of doing this, as we've heard from previous speakers, there are all kinds of quality indicators that we're concerned about. But for this purpose, the quality characteristic that's of primary concern is the magnitude of the difference between what we should have reported for a patient and what we do report. The larger that difference, the poorer the quality of the result. And one way that we can characterize that or quantify it is to look at the probability of producing a result that exceeds some allowable error specification. We've heard talks earlier about how to define allowable total errors or total allowable error specifications. So the idea here is that if we produce and report a result where the difference between what we should have reported and what we do report exceeds the allowable total error, we consider the result unreliable or incorrect. And if it's smaller then the idea would be that an unreliable or incorrect result has the potential to create a hazardous situation that might lead to harm to a patient. So it's, if we think of the shaded gray Gaussian distribution as reflecting measurement error for a process that's operating as intended, so the x-axis is measurement error. In this particular case, it's centered on 0, so we're assuming no inherent bias in the process. If we consider the dark Gaussian distribution shifted to the right as the state of the process because of an undetected out-of-control condition that's resulted from some failure mode, then we can compute the probability of producing a result that fails to meet its intended use by determining the area under that curve that is outside of our allowable error specification. And in fact, we can do that for every possible magnitude of out-of-control condition that might occur, and we can generate a curve that looks something like this. So P subscript capital E here is meant to represent the probability of a big E, a big error condition, so probability of an unreliable result. And we can see that, and the x-axis is the true state of the testing process. So a value of 0 here means the process is in control, and a value of 1 here means that there's been a systematic shift in the process that's equal to 1 analytic SD of the process. We would expect that if we have good testing processes, that the chance of producing unreliable results when the process is operating as intended should be very, very low. So we would expect that this curve starts out at a value that's very small when the process is in control. And certainly for large enough out-of-control conditions, the probability of producing unreliable results can approach 1. Okay. So that's the way we'll define and quantify the risk of reporting, or producing and reporting an unacceptable or unreliable result. Now, the key outcome measure that I'm interested in to try to relate what we do in the laboratory in terms of quality control and the risk of harming a patient is the expected number of unreliable patient results that will be produced in the event of an undetected out-of-control error condition. So in this cartoon, which appears in a lot of the figures that in papers that I've published recently, the horizontal line is meant to represent time. Each individual little vertical line is representing a patient specimen that's been tested, and the diamonds represent the points where we test quality control and make a decision about the state of the process. If the diamond's shaded green, that means that our quality control rules conclude that the process is operating as intended, and if it's shaded red, that means we get a QC rule rejection. Okay? So the idea here is we're going along, we're in control, and then at some point in time, failure mode causes an out-of-control condition that results in a shift in the process, so that on average we're producing results that have a constant bias in them. The number of unreliable results that will be produced during the existence of that out-of-control condition will depend upon a number of things. It will depend upon the type and the size of the out-of-control condition. That will determine how many of those vertical lines have a red asterisk above them. The red asterisks are meant to denote those patient results that are unacceptable, that are unreliable. The larger the size of the out-of-control condition, the more of those vertical lines we'd expect to have red stars above them, because it's a larger error condition. It's also going to depend upon how good our quality control rule is at detecting the out-of-control state, the power of our quality control procedure. The more powerful the rule, the fewer tries it should take before we detect that we have a problem. And then thirdly, the thing that and the focus of this talk, the number of unreliable results produced during the existence of the out-of-control condition is going to depend upon how frequently we test QC. If we test QC, if we have more patient specimens between QC events, they're more likely to have, we're going to have more red asterisks during the extent of that process, right? So, we've seen this slide before, and now I've added in the right column ENU, which is, I didn't specify, it was in the title of the last slide. That's what I used to represent the expected number of unreliable results that were produced because of the existence of an out-of-control condition of a certain size and magnitude, or a certain type and magnitude. So what we do when we're defining, or what we can do when we're defining our quality control strategy is ask, given this quality control strategy, given these rules and this frequency of testing, what would be my expectation for the number of unreliable results that would be produced during the existence of an out-of-control condition of a certain magnitude before I detected it? Okay. Now, how many of those unreliable results that are produced end up being reported and potentially causing harm will be dependent upon how quickly we detect the condition and when we report results. So, come on. Now we're told, again, there are three things that can determine how many unreliable results are produced and reported, which is the magnitude of the error, which we don't have any control over, the quality, the power of our QC rule. That's the thing that we typically tend to look at, is how powerful is our QC rule, and the frequency of QC testing. And this session is on frequency, so that's what I'm going to focus on, not the others. And we can think, when frequency of testing is really all about when do we schedule QC. And we schedule QC two different ways in the laboratory, which I refer to as event-related QC and an event-independent. So the idea with event-related, as was alluded to by Niels, is we understand that there are certain critical control points in the process where we may be concerned that a change can occur because of that critical control point. And we want to test QC to assure that something hasn't changed at that point. I call that event-related QC testing. The frequency is determined then by those critical control points and when they occur. We don't determine that. That's determined kind of for us. In those cases, we almost always will test QC immediately after that critical control point to assure that something hasn't changed. I would argue that that's a legitimate thing to do, and that the focus of that is really an instrument focus. We're concerned about the instrument, whether or not something's happened to it. I would also argue that you should be, when these critical control points are known in advance, you should be testing QCs immediately prior to that event. I would say that's a patient focus. The idea there is that I want to test QCs to assure that all the patient results that have been produced and reported since my last good QC are reliable. Okay. In fact, this was one of the recommendations that came out of one of the working groups from last year's experts meeting. And it appeared in the opinion paper, which is that QC testing should not only follow calibration, but should immediately precede calibrations, just for this reason. If our focus is going to be on the patient, one of the previous speakers said, our focus should be on the patient. If our focus is going to be on the patient, then we really need to be testing QCs prior to critical control points that might change the process, as well as immediately after them. I'm not really interested in event-related QC for this talk. I'm interested in what we do between those critical control points. How do we decide when to test QCs between those critical control points? What frequency do we use? Now, you can think of frequency in two ways. Time, I'll test once a day, I'll test once every 8 hours, or the number of patient specimens between QC events. From the perspective of patient risk, it's the number of patient samples between QC events that's the critical key, not time. Now, when we detect an out-of-control condition, ISO tells us that there are some things we have to do. We have to halt the process. We have to take corrective action. And then any results of non-conforming examinations that have already been reported need to be appropriately identified and corrected if possible. As I'll call this recovering from an out-of-control condition. So if we go back to the cartoon I looked at before, we can think of that period of time where the process is in an out-of-control state and break it into two intervals. That section that was from the occurrence of the out-of-control condition up until the last QC event that passed. They gave us an acceptance signal. And then the interval from the last good QC to the place where we detected it, where we got a QC rule rejection. I refer to the first as the pre and the second as the post. Pre-last good QC event, post-last good QC event. The idea here would be if we're holding results and releasing them only after we get an accepted QC, then that post period would never get reported. There would have been unreliable results that were produced, but they would have never been reported. Okay? If we're immediately reporting results as soon as we get them, then what ISO and others would say is that those results, at least back to the last good QC event, are the ones that we should try to identify and correct. And if we can do that in a timely fashion, then we can think of that as a result that wasn't a final incorrect result that was produced. So now we really have, in terms of looking at the influence of frequency of testing on the risk of producing an unreliable result that might cause patient harm, we kind of have the conceptual model that we need. It's not a difficult conceptual model. I've heard people talk about how, yeah, we recognize now that frequency of testing is an important issue, but that's a complicated topic, and some people are working on it, but we haven't figured it out. It's really not that complicated. Conceptually anyway, it's not that complicated. The number of patient samples between QC events are going to influence how many bad results get produced when an out-of-control condition occurs. Okay? Now the question just becomes, can we predict or compute or estimate what the implications are given a particular quality control plan in terms of what it implies for the risk of producing unreliable results that were prior to the last good QC event, which means they probably are incorrect, unreliable, have gone out and will never be corrected, and those that have been produced since the last good QC event, which maybe never get reported, or if they did get reported, maybe can be corrected before they cause a hazardous situation that results in harm. Well, it turns out computing the things isn't that difficult. It's not a lot any more difficult than computing a power function graph. Not that all of you go out and compute power function graphs every day, but there's nothing really any more complicated about the mathematics or the simulations to compute these things than is required for computing all the power functions that are out there in the literature. So here's an example. The top figure shows two curves. The blue curve on the right is one we've seen before. That is representing the probability of producing an unreliable result in the presence of an out-of-control condition of a given magnitude. Okay? That curve depends upon our total allowable error specification and the performance characteristics of our method in precision and bias. Okay? So we can't compute that curve without specifying an allowable total error. The green curve on the right is reflecting on average how many patient samples are produced while an out-of-control error condition occurs up to the last good QC event. That curve is going to depend upon the answers to the three questions of what rule, how many QCs do I test for the rule, and how many patients do I test between QC events. Okay. So because it's the average number of patients produced, it's a number that, for very small out-of-control conditions, is going to be large because it's hard to detect very small out-of-control conditions. And as the out-of-control condition gets larger and larger, the chance of us detecting it the first time is high. If we detect it the first time, then there are no unreliable results prior to the last good QC event because there were no unreliable results produced prior to the last good QC event. The product of those two curves, how many on average results were affected times the probability that they're unacceptable, produces the lower curve, which is the expected number of unacceptable results that were produced prior to the last good QC event as a function of the magnitude of the out-of-control condition. Now, we don't know what magnitudes of out-of-control conditions might occur in the future, but if we look at a curve like this, what we could say is if for this particular situation with my allowable error specification, whatever it is, and my QC plan, whatever it is, I would never expect more than 2 unacceptable results to have been produced prior to the last good QC event. Okay? So that gives me some knowledge that I can use to try to manage things. The expected number of correctable unreliable results is the expected number since the last good QC event, so in that last interval. And here things aren't quite as nice. This really is mostly a function. So again, the blue curve is the same as in the last figure. The green curve is the average number of patient samples that were affected by the out-of-control condition since the last good QC event. And it really only ranges from the total number since the last good QC event to half of that. So in this case, I must have been assuming 100 patient samples between QC events. Okay? So when you multiply those two curves, you get something that starts low, increases, and flattens out at a value that's 1/2 the number of patient samples between QC events. So this number, this correctable number, is really simply a function of the frequency of testing, the scheduling of QC. It doesn't really have too much to do with the power of the QC rule. So I've added another symbol to the right on this figure. So we can compute for a given QC plan for different magnitudes of out-of-control condition for different types. So the only type I've looked at here was a persistent out-of-control condition. We can compute the unreliable results produced, the expected number, that was the total number of red stars. And we can also compute the expected number that were part of the last good QC event. Those were the ones that would most assuredly have been reported and probably never corrected. If we're doing bracketed QC, that would be it. If we're doing immediate release, it might be somewhere between ENUF and ENU, depending on how many of the unreliable results since the last good QC event got corrected in a timely fashion. Okay? This is the thing that we can try to manage. We can decide on a QC plan to try to assure that the expected number of unacceptable final results doesn't exceed a value that we're willing to tolerate. Now, what value are we willing to tolerate? Okay, well, that's going to maybe depend. It's going to depend maybe on what our information or assessment is of the likelihood of an incorrect result resulting in patient harm. We don't have control of that part of it, but we can certainly be informed about it. So if our assessment is that this is a situation, this is an analyte used in a particular situation where if we produce and report an incorrect result, it is most assuredly going to lead to patient harm, then we might want to manage that expected number of incorrect results that we report at a much lower level than another situation where our assessment is that, you know what, we could produce and report 100 incorrect results, and maybe only in one of those 100 cases will we expect it to lead to harm to a patient, in which case we might be willing to tolerate more unacceptable results being produced and reported. What I'm trying to say here is that I don't want to tell you what that should be, but it's not like there should be a one-size-fits-all. You really, as laboratory professionals, should have some input into how to manage that number in a way that makes sense for the analyte and the patient population that you serve. Okay? So, my last slide. So, quality control is needed. Why? Because clinical diagnostic processes fail. We are the instrument manufacturers with risk management and with risk management guidelines in the laboratory. We're doing a better and better job of trying to identify potential failure modes and reducing their occurrence. But when it's all said and done, our processes fail. Okay? And we need quality control because of that. The impact of process failures should be assessed in terms of the risk of reporting unreliable patient results. I wrote a paper last year in a journal called Advance, where the title was that quality control should focus on the patient, not on the instrument. I think for too long we tend to focus on controlling the instrument. We're controlling it with an understanding that poor performing instruments lead to bad results that might affect patients. But our focus should be with the end in mind. We should be focusing on the patient and then determining how to control our instruments in a way that assures that the risk of producing and reporting unreliable results is low or is manageable to a level that we're comfortable with. The frequency of QC testing, the number of QCs examined, and the QC rule all impact the expected number of unreliable patient results that will be produced during an out-of-control condition. You can't ignore frequency. Number of controls and the control rule are fine for determining how likely you are to detect an out-of-control instrument, but it's not enough for determining the risk of producing and reporting unreliable patient results. You need to know the frequency also. It's not only possible, but it's not all that difficult to design QC strategies to manage the expected number of unreliable patient results that are produced and reported when an out-of-control condition occurs. And what's considered acceptable should probably depend upon our assessment of the failure mode rate and the likelihood of patient harm resulting from an unreliable patient result. And with that, I thank you for your attention. Wait, hang in there, and I'll be back for my beer in just a second. Thank you.